Yeah, so good morning, good evening, wherever you are based. My name is Antti Lehikoinen, and I will be giving a presentation on high-performance electric motors, some of their challenges and solutions from a physics-first perspective. So, my background is I'm a consulting engineer running my own single-person business, matlab, since 2017, which is the same year I got my PhD from Aalto University, Finland. And I have been happy to work on quite diverse applications ranging from EV traction applications to aviation, high-speed machines, special machines, stuff like that. Then additionally, I develop and distribute and use my own software, which is a toolbox for MATLAB focused on electric motor design and analysis using finite element analysis. And I will incidentally be giving a tutorial on that on Monday. So hope you will be there and check it out. But let's move on to our presentation here. What I will cover today is the definition of high performance in the context of this presentation, then how to actually reach that high performance that you are after. And I will be taking a physics first or first principles approach here. So I hope it should be understandable even if you don't have that much experience on motors per se. And finally, I will be looking at some challenges or roadblocks on the way towards high performance. I may have to skip some material, so please reach out to me later by email or on LinkedIn or whatever if needed. So let's define high performance. Of course, it's highly context specific. We will be speaking about traction today, where high performance is usually understood as a combination of efficiency and power density. But in other applications, for instance, servo motors, it might mean fast response time, small torque ripple, high precision. In a dentist's drill, if it were powered by a motor, I think some of them are, it might mean a low noise, low vibration behavior, stuff like that. But anyways, today's focus will be on traction. So a combination of efficiency and power density, and especially power density today. And I will be particularly looking at ground mobility applications or mobility applications like ground aviation and boats. So how to reach that high performance? We will shortly take a look at the underlying physics, the first principles behind it, see what would ideally make a high performance machine, and then how to reach that in practice and what kind of challenges have to be overcome there. So let's start with the very basic physics. We know that power equals velocity times force. So the faster you go, move something with a given force, or the higher force you can exert, the higher the power will be. That's basic physics. When you move down to motors, there are some specifics that you have to consider. For instance, instead of velocity, the V, it's not any velocity we are speaking here, it's the surface velocity of the rotor or the rotating part of the machine. Or if you have a linear machine, it's the linear motion of the mover. So that's the velocity. And if you have a rotating machine, it's proportional to the angular velocity in term proportional to the RPM, revolutions per minute. and the diameter or radius of the rotor. Then the force, then what it's coming from is magnetics, of course. There are many ways to compute the force, but in my opinion, the easiest to understand on a conceptual level is go back to high school physics, where you may remember the Lorentz force. When you have a current carrying conductor and a magnetic field, a force will be induced on the conductor. And it turns out you can use the same force equation for machines with suitable definitions of the terms. So you have the Newtonian flux density. And then finally, you have the current. Current alone can be confusing. So I like to write the net current as a product of the current density and then the total area, the total current carrying area or volume of copper. So you finally end up with this kind of equation. You have the surface speed proportional to the RPM and the diameter, and then the force proportional to the length of the machine, flux density, and then the current density times conductor area. So if you want to reach high performance, that's the goal here. Let's try to reach high power first, and later we will see what happens to the efficiency with some of the approaches. If you want to increase power,
did we lose him, guys?
Trade-offs, none of them can be really adjusted. So also, just a side note, please note that the voltage, high voltage, is not included in this equation. It can be beneficial for high performance machines to increase the voltage level, but it's not a first order effect. There are like second order complications only, through which it can make things easier. For instance, you can use smaller conductors, which helps to reduce the AC losses or eddy current losses and increase efficiency. And then your cables and coil connections, they can get smaller and lighter when you have a higher voltage and smaller conductors. And finally, maybe the biggest reason for EVs is that battery management can get, well, the battery management per se gets harder, but other stuff like the charging and cabling, they get easier when you have a higher voltage. But let's go back to the main topic here. So high power and trade-offs. You can increase any of these factors, but whenever you gain something, you will either hit an obstacle or lose something. For instance, if you increase the RPM, there are some mechanical limits and gearing that you have to consider. For the rotor radius, you increase the size or the diameter of the machine, the mass of the housing. Again, you will hit some mechanical issues. If you increase the length, well, you simply have a bigger machine, and the so-called bending vibrations can get problematic, and so on. For flux density, you can't really do much about it. And for current density and conductor area, there are losses, manufacturing issues, and cooling to consider. And to make things worse, most of these are intercoupled. So next, let's take a look at each of these. So what kind of trade-offs you will have to be prepared to make or prepared to tackle when you wanna increase the power of the machine by this first principles approach here. So let's look at high-speed machines here, because the first term in this power equation that we saw many times is the surface speed of the rotor. And you increase that, you increase the power of the machine. And I would argue that it's one of the easiest ways, if not the easiest way, to increase the power density of a particular machine without killing the efficiency at the same time, up to a limit, of course. So let's soon see why it works and what happens when we increase the surface speed, and also what happens at the same time when we increase the surface speed. So as we saw, the surface speed is the product of the angular velocity and the rotor radius. And you can split this term open and write it with the RPM, or the electrical frequency F, and the number of pole pairs. Basically all and each of those numbers or parameters, they get thrown around a lot when folks are speaking about high-speed machines. But it's important to remember that as a first-order approximation, none of them increases the power of the machine without increasing the surface speed. If you keep the surface speed constant and change two of them, for instance, you increase the diameter of the machine and reduce the RPM, nothing happens as a first principle again. If you keep all other factors constant, there are of course other effects and higher order effects. For instance, when you increase the pole count, this P here, you need a higher frequency to stay at the same RPM, but that's difficult. That's problematic, but at the same time, you can decrease the iron mass, can reach higher so-called electrical loading of the machine, which again helps to increase the power density without leading to issues with magnetic saturation and so on. But these are, like mentioned, second order effects. So let's now see what happens actually when you increase the surface speed. So we already know that the power, it increases. Then it depends on how you increase the speed, like what kind of secondary effects you will get. If you simply increase the RPM here, nothing happens. As a first order approximation, of course, your machine will be spinning faster, so you need gearing and so on. And then there are mechanical issues that we will be seeing soon. But electromagnetically, nothing else happens. The frequency gets higher, and that's all. If, on the other hand, we increase the diameter or radius here, then the machine gets bigger and the geometry will change. You will have to make some decisions. Are you gonna be scaling all the dimensions equally proportionally to the radius, or are you gonna be changing something? Both are options. Usually you will have to change something, or sooner or later, if you keep increasing the radius, you will have to change something. But anyways, it's a more complex relationship. What usually happens is that the power per the active mass of the machine, like the magnetic components, winding, electrical steel, any magnets if you have there, the power density with respect to the active mass does increase. However, the mass of the housing that the machine is often inside of Of course, there are frameless machines, some jet applications where the machine might be built into a jet engine directly, where this does not apply. But if you have a housing, then the mass of the housing, it will usually increase faster than linearly with the diameter. So at some point, it will start penalizing your power density. And the same happens to the shaft of the machine, unless you have a hollow shaft or almost hollow shaft, which is again possible, but mechanically tricky, might be difficult to manufacture, so on. So that's what happens to the power of the machine and to some degree the mass of the machine when you increase the surface speed. Now, let's see what happens to the efficiency. I mentioned maybe earlier that high-speed machines are often quite high efficiency machines as well. Per our definition of high performance machines, they are exactly that. So now let's see why that happens. So the efficiency by definition is the output power divided by the input power, if we are speaking about a motor. And the input power is the, okay, I have a typo here. The input power is the output power plus losses. And we already have our formula for the output power, the mechanical power here. Let's just plug it in. And then for the losses, let's consider the iron losses and the winding or copper or resistive losses here. So the iron losses, they are proportional to the electrical frequency. So the number of pole pairs times the mechanical speed to the power of something between 1.5 to 2.2 usually. It's a complex relationship, as you may know. And then the winding losses, well, we can get from high school physics earlier. It's the familiar Ohm's law, Ri squared formula, which can be again written with the conductor area A and the current density squared. So what's the important implication here is that when we increase the current density, when we increase the surface speed and the output power, the winding losses here stay constant. So our efficiency improves if nothing else changes, unless we go crazy high and these iron losses start to dominate badly. But let's just for now assume that they stay manageable. So if we simply increase the speed and change nothing else, our efficiency improves, meaning we can at the same time increase our current density, this J here, somewhat by some degree without killing the efficiency, because with the speed increase, our efficiency just improved. So we have some way to reduce it again by increasing the losses. And we can, well, that's what happens when we increase the current density. But at the same time, again, the output power increases. So it's a rare example of a nice positive feedback loop, I would say. You increase the surface power, you increase the power density, and you then can increase the current density and increase then the power and power density even further. So that's a rather nice thing. Of course, there are physical limits. We will see them now. So what are some of the drawbacks of high surface speed? Well, there are physical limitations. For instance, the centrifugal forces or stresses in the machine or in the rotor of the machine, they grow proportional to the speed squared, basically. meaning things get more and more difficult the higher you increase the speed. Meaning if you have a surface permanent magnet machine where the magnets are on the rotor surface, you can't hold them in position with simple glue alone, but you will need some kind of sleeve, retaining sleeve on top of the rotor. It can be glass fiber for modest speeds, or if you go beyond 50, 100 meters per second, it has to be either carbon fiber composite or some metal alloy. And both have their own benefits and drawbacks. Carbon fiber is very strong and light, and it's not very conductive electrically. So there won't be any like AC losses induced in the carbon fiber composite. But on the flip side, it's also an insulator thermally speaking, meaning cooling the rotor just got more difficult. And when you have magnets in the rotor, you very, very much have to cool them, because otherwise you will simply kill your machine if you overheat your rotor. On the other hand, if you have like a metal alloy sleeve, like some titanium alloy or Inconel or stuff like that, it's very conductive thermally. That's a good thing. Also, its thermal expansion coefficient is similar to that of the rotor, so you won't have any expansion fitting issues there. The flip side is that it's also electrically conductive, meaning you will induce high eddy current losses in it very, very often. So that was for surface permanent magnet machines. If, on the other hand, you have an IPM, like in the picture here, well, the magnets, they are embedded inside the iron. That's where the name comes from. And you have to have some kind of thin iron bridges to hold them in place, to stop them from spinning away. Now, when your speed gets higher and your stresses get higher, those bridges, they have to get thicker and thicker to be mechanically strong enough. And what happens then is that more and more flux, more and more of the permanent magnet flux will start escaping through those bridges, which again is a bad thing. You don't want your flux short-circuiting itself like that. You want it to go to the state and link the winding so that it can do something useful. If it's just circulating within the rotor alone, it's just wasted magnet material, wasted flux. So if you increase the RPM of the machine, you get some extra issues in addition to those with the high surface speed. For instance, you have to consider the RPM at which your load is spinning. If you are running a turbine or running a generator with a turbine, then it's likely that things will be spinning quite fast by nature. So a high RPM is actually desirable. In that case, you can avoid a gearbox altogether, which is a nice thing. On the other hand, when you are inside an EV, you will very much need a gearbox, a reduction gear. The wheel of the vehicle might be spinning like, I don't know what, 1000 RPM at tops. So if you have a 20,000 RPM machine on the other end, you will need a reduction ratio of 10:1, which can be a rather large gearbox with its own losses and all its own issues with the construction and cost, yada, yada, yada. Then also bearings. Bearings can get difficult beyond maybe 20k RPM or so. And finally, those bending vibrations that I mentioned earlier. Basically, what is meant by bending vibrations is that, well, when you have a shaft with a rotor supported by two sets of bearings, one at both ends, there will be a resonance mode where the shaft is bending a little with the rotor, and it will have a certain resonance frequency. And it turns out you don't wanna spin your machine close to that frequency, because when you do, or let's say if you do, then any mass imbalance in the rotor, and you will always have some. It's very difficult to have a perfectly balanced rotor. So when you have a mass imbalance and you are rotating close to the natural bending mode, the mass imbalance, the centrifugal force caused by it, it will start exciting the bending mode, and basically your shaft and the rotor set will start vibrating. So, and that's not a good thing. That's something that you definitely don't want. So ideally, you would operate your machine below the first bending resonance. And I have here the formula for the frequency of the bending resonance. So you see you have the radius or diameter of the rotor and then the length of the machine. So if you increase the length, you pretty much decrease quite significantly the first bending frequency, meaning it's easier to excite that accidentally. Or if you increase the RPM of the machine, you obviously get closer to the bending frequency that is staying fixed. Finally, I mentioned that high RPM usually leads to high electrical frequency. It also has its own issues. You have to be able to supply the machine somehow with an inverter, and nowadays they are usually limited to 1 or low kilohertz range for high power applications. Also, I mentioned the iron losses start to grow quite fast with the frequency. It can be helped by using thinner iron laminations, for instance, thinner than 0.3 millimeters, something like 0.2, 0.12, 0.1 even, relatively common already nowadays. But still, they are costlier, they are more difficult to handle, meaning the assembly gets more difficult and more costly, and so on. And finally, you will start to get higher and higher AC or eddy current losses in the windings of the machine. You can eliminate them quite nicely by using leech wire, which is visualized here. But again, it's costly, it can be difficult to source, difficult to assemble, so on. Or you can simply use stranded windings, so lots of thin wires connected in parallel. But in that case, you can and you will have some circulating current losses where you have an uneven distribution of the current between all those thin wires. And those are nasty in the sense that they are very hard to predict because they are a statistical random phenomenon. So they vary from machine to machine. So even if you build a single prototype, you can't guarantee that the losses will be nearly similar in the next 10 machines you are gonna build. So, like mentioned, they can be nasty. So that concludes the part on high-speed machines. So if we don't want to increase the surface speed of the machine, what else can we increase to increase the power and maybe, hopefully, the efficiency, or at least not kill the efficiency while we are doing it? So it's basically any of the other 4 factors that we have here. Some of them are easier to increase, some of them are harder. For instance, if we increase the length of the machine, well, we have a longer machine and that's it. It's a bigger machine. We increased its power, but we increased its weight or mass by pretty much the same. Same factor, and we didn't do anything in its efficiency. So for power density or efficiency, it doesn't really help. Plus, you remember that bending vibration thing we get, I spoke earlier. So when you increase the length, you decrease the bending frequency, meaning you can't operate your machine at higher RPMs anymore. Okay. So the next factor is the flux density. Well, it's something that you simply cannot increase because the flux density or the flux in the air gap of the machine, remember this is the air gap flux density, it has to go somewhere, and that somewhere is the iron of the stator. And on the iron side, we have material limitations, how much flux density the iron can carry, so to speak. Normally, it's about 1.8 Teslas for common materials before you start to heavily saturate your iron. If you move to cobalt iron, you can shift it up to 2.2 Teslas or something, pay an absolute ton of money for that. And as you can see, the performance gain is quite marginal, to be honest. So what else to increase? Well, you can increase the area of the conductive material, but you have to remember that the conductors, they have to fit somewhere. They have to fit inside the slotting of the machine. You can't really make the slots any wider because then you would be cutting the teeth of the machine thinner, meaning you would have to cut the flux density to be able to fit that inside the iron in the teeth. Or you could make the slots deeper again, but then you would simply be increasing the size of the machine. So if you want to think all other aspects constant and simply increase the copper area or the conductor area, your only choice is to improve the packing of the conductors. Basically fit more copper or conductor area inside a fixed volume. And there are a few options for that. You can use rectangular conductors that are easier to pack. I think hairpin is the term that most people are familiar with nowadays. Hairpins are simply a special kind of rectangular conductors that also have that one plus side that they are quite well suited to fully automatic production with robots and laser welding and so on. So they work nicely for series production, and incidentally, they also improve the packing of the conductors because they are rectangular, they are easier to fit there inside the slots of the machine. The flip side is that when you go to higher frequencies, and like we saw earlier, to reach very high power densities, high speeds and high frequencies, they are often beneficial. Well, rectangular conductors, they can't really go very high, at least with the current manufacturing capabilities that are widely used now. The practical limit is at around 600 Hertz or 1 kilohertz or so. The reason being that the conductors, they need to get smaller and smaller when you move into higher frequencies, and then you also have to transpose or twist them suitably, and that can be tricky with rectangular conductors. So they still have their limitations.
Just a quick question. Sorry to interrupt. One quick question, just to sneak one in. Again, this is not my domain at all, but I see the equation at the top, and you're walking us through, ways to increase the power through these variables. Just a question: where does sort of the new chemistry come in? In which one of these variables does new chemistry come in? Like silicon anode cell chemistry, this stuff that the folks are researching for for higher density, is that a variable? Is that part of one of those variables indirectly by proxy, or is it represented there somehow?
Well, it depends on what you mean by new chemistry. If we are speaking about the materials that are used in motors, there are a few options. The first one is what is actually mentioned here, are the insulation materials. Like if you can have thinner insulation, like insulation is needed to basically prevent short circuits in the winding between the wires and conductors or the...
Oh, you know what I was thinking about, and I got confused. I was talking about the battery as a source of energy. And if everything is constant in the motor and you don't want to redesign your motor, isn't the innovation in the battery another source of power or not?
On the motor side, not really.
Okay.
Because, well, the batteries, they have to be able to supply a certain power, and they do it at a certain voltage, meaning they have to be able to deliver a certain current. But the motor itself, it can be quite flexibly redesigned for a different battery. It's especially as a first order approximation, the kind of battery that you have, it doesn't really influence the motor design that much, as long as the battery can deliver a given power.
Oh, okay. So you're assuming that there's a battery that's giving a certain power, and then what can you do? Okay, fair enough. Thank you. That's helpful for me. Thanks.
Yeah, sure. That's a nice question. But anyways, like I mentioned, insulation, some kind of insulation is needed between the conductors and the iron, and between the different conductors, and it has to be of certain thickness, usually some 0.2 millimeter, something on that level. Could be small, could be higher, could be smaller, but something is needed. And again, that's eating away some of the space that could be used for conductors. So new, better insulation materials, so that they can be thinner without breaking down. They can slightly increase the power density and power. And finally, the third option are so-called compressed coils. These are nice that they are also suitable for high frequency applications. So you can, for instance, make a conductor out of a lead wire and then compress it into smaller space, meaning you can squeeze the different wires very close to each other. What is seen here in this beautiful paint circling in red that I have here, that's an example of a compressed lead wire. And I don't know if it's very visible, but there are some, maybe a few hundred wires in each of those slots. Lots of small circular copper wires. And as you can see, they are very closely squeezed, close to each other. And that thicker black area that you see between the bundles of copper and between the steel, that's the insulation that I was speaking about. But let's move on. The final thing that you can increase is the current density, J. And it turns out it's a often a very good solution, at least from the electromagnetic point of view, because you see that the power, it increases linearly or proportionally to the current density. That's a nice thing. And if you remember the efficiency formula earlier, well, yes, the losses, the winding losses, they will increase proportional to the current density squared. So what typically happens is that when you increase the current density, you will hit your efficiency, but often not by a colossal amount, especially if you are, again, operating at a high enough surface speed. Then, depending on your ion losses and mechanical losses, it may actually turn out that your efficiency increases when you increase the current density, because again, you are increasing the power output of the machine. And if your winding losses are not that significant in the beginning, then increasing them by somewhat by increasing the current density is not a dramatic issue. And indeed, the current density is often not limited by the magnetics themselves, but it's by cooling and thermal aspects, how you can cool the machine, get rid of the losses in the winding. Like, remember, the loss density in the current carrying conductors is proportional to the current density squared. And for that reason, our final topic today will be the thermal management of machines. And again, some higher end, high performance approaches will be briefly covered. Again, we have this power formula here, and our previous conclusion was that increasing the current density is a good way to increase the power output without killing the efficiency, if and only if you can keep your machine motor generator cool enough at the same time. So, thermal management, basically, it consists of two components. First is the actual cooling, also called heat extraction, getting the heat out of the motor. It's normally of supreme importance, because when we have a high performance, high power density machine, it pretty much always also has a high loss density. It has high losses per unit volume or unit mass, unless its efficiency is crazy high at the same time, but normally that doesn't happen. So high power density machines are also high loss density machines, meaning they are hard to cool, and they will have to be cooled very efficiently all the time. Otherwise, they will simply quickly overheat and die. So that's the critical part. The second part is the so-called heat rejection, getting rid of the heat. It can be easy, it can be hard. For instance, if you have a boat, an electric boat, for instance, it's very easy just to dump the heat into the sea or lake that you are riding. That's the easiest solution. If you have a car, it can be more difficult because you need a radiator of some kind. Luckily, the combustion engine folks have been building radiators for about 150 years now. So we have lots of collective experience on that front. So we are not starting from scratch. Anyways, our main focus here will be heat extraction. And within that topic, our main focus will be the windings, because they are normally the most critical component. Normally, they have the highest loss density per volume. And additionally, the average or bulk thermal conductivity of the winding as a whole is very poor. It's bad. Copper, the conductor material, that's a good thermal conductor, yeah. But you have insulators, insulating material surrounding the copper. And they are electrical insulators, yeah, but sadly, they are normally also very good heat insulators, meaning the bulk conductivity of the winding is usually between 0.5 or 2 watts per meter Kelvin, which is like 1/10 or less of the steel, the conductivity of the steel of the machine. So the windings, they are the critical component. They have a high loss density and poor conductivity. So what approaches are used nowadays? Maybe the most common approach after simply air cooling is the water jacket, where you basically have some fluid, usually water, could also be oil or something, circling in the housing of the machine. So it's not in direct contact with any of the active parts, but it's surrounding the machine. It's like the traditional quote high performance approach, and with it you can reach something between sub 10 to 20 amps per square millimeter. The common rule of thumb is like 15, but I wouldn't trust that because it depends so much on the size of the machine and the winding packing and stuff like that. So that's like the easiest, most common high-end approach, let's say. The second most common is the so-called spray cooling. It's used in a few EVs, tier 1 EVs nowadays at least. Basically what happens is that you are cooling with oil and you are spraying it on the end windings of the machine. So the end windings are the part of the winding that is not inside the active part of the machine, but they are the visible part. And what is spray cooling? When you spray them with oil, the oil takes away some of the heat, then it's collected at the bottom of the machine. They have a sump or something, then it's fed to a radiator, for instance, and recirculated back into the machine. What it does, it obviously takes out some heat from the end windings, usually lots of it, which is a good thing because the end windings, they are usually the hardest part to cool because they are normally in air. And the convection into air is not a very efficient means of cooling, but the spraying these end windings basically solves the end winding cooling issue. It can also pull out some heat from the active region of the machine, more or less, again, depending on the geometry of the machine. Then a newer modification of this is basically a combination of direct core cooling and spray cooling. This is used, for instance, in the new Lucid Air motor. Maybe you have seen the video that I took this screenshot of. What they have is basically they have this kind of a cooling channels cut into the stator core of the machine. And then in the axial center of the machine, they have this kind of a groove here. So they are pushing oil in here, then it splits into the both axial directions. It flows biaxially via these cooling channels. And then while exiting this machine, it also sprays the end windings. So it's like a combination. It's almost like a water jacket, but the fluid is running inside the active part of the machine and not the housing. And then on top of that it's also spraying the windings. Finally, if we go to even high performing approaches, we have so-called submerged cooling, where we have the entire stator flooded in oil, and inside the bore of the machine, we have a can of glass fiber or similar plastic, composite, stuff like that, meaning that the oil doesn't flood the rotor, because the rotor, it has to be spinning at a high enough speed, and you can't really do that if it's submerged in oil. So only the stator is flooded, and you have oil running through the stator. Usually you have channels inside the slot region cooling the winding. You can have one of them or several, and also you might have something in the core of the machine too. What kind of current densities you can reach with this one are about 25 amps per square millimeter. That's the common value that is quoted in the literature. Again, depends on the size and type of the machine. So that's the best, like, semi-mainstream approach that we have nowadays. It's not very commonly used in any series produced machine as far as I know, but it's like semi-commonly used in high power prototypes for aviation and stuff like that, at least. And then finally, we have some even more advanced and future approaches. One is to use hollow conductors, like what we have here, where we have coolant running inside each conductor. That is very, very efficient. You can reach current densities up to 60 amps, perhaps even higher. But again, assembly regions, the size, physical constraints, basically dictate that your conductors, they have to be so large that you can't really move close to 1 kilohertz, let alone beyond it. So they are more of a curiosity, very useful for some applications, but for very high-speed machines, probably not very useful. So in my opinion, what we do need is a modification of either this flooded or submerged cooling or this one here, but we need to have those cooling channels running directly inside the slots of the machine. And we need to have several of those, at least 3, probably like half a dozen, tens, stuff like that. Because again, remember, the bulk conductivity at the winding region is very poor. So if you wanna push the current density higher, then the nearest heat sink, it has to be very close, no matter which physical location inside the winding region you are, or the nearest heat sink, the nearest cooling channel, it has to be very close. So then you would have to like uniformly space them inside the slots. So how to do that? Well, the jury is still out on that respect, but stuff like additive manufacturing might be slowly getting there. It can't really do very small conductors, something like 1 millimeter might be practical nowadays, but it's getting there. So maybe in the next few years, half a decade, it might begin to be like an actual game changer for this kind of applications, but maybe not just yet. So we are nearing the end. Let's move on to the conclusions. These are very short. So basically what I showed you was an overview of high performance machines, electric motors and generators, defined as machines combining a high power density to high efficiency. And we saw that a high performance usually comes from some combination of 3 factors. One was the rotor surface speed, perhaps the best way to do things if you can handle the mechanics and if you can fit it in the overall application. And the second option was increasing the current density and taking care of the cooling, and finally increasing or improving the packing of the conductors inside the slots of the machine. Okay, I think we are nearing our end here. We have time for maybe 1 or 2 questions, if we have any. Do we have any?
I don't think so, Antti.
Okay.
Maybe last comments, maybe Monday we will have a live demo, right, of your tool, maybe a few words on that.
Yeah, so on Monday, like mentioned in the beginning, I'm a consulting engineer running my own business, and I also develop and sell a MATLAB toolbox for electric motor design based on finite element analysis. And I will be giving a demo and a workshop of that on Monday. For instance, these pictures here have been computed. We have the flux density map of an IBM machine and then an efficiency map of I think it's the same machine. So yeah, hope to see you there.
Amazing. Great talk, Antti. Thank you so much.
Thank you.
Especially doing it at night.
Yeah, sure.
Thanks. Really great. Any questions from the audience?